Module 2, Lecture A, Big O Basics. By the end of this lecture, you will be able to explain the meaning of Big O, Big Theta, and Big Omega in the context of algorithm analysis. Determine the time complexity class of simple Python functions by inspecting their structure. And compare two algorithms using Big O notation to justify which is asymptotically more efficient. Asymptotic notation essentials. Big O upper bounds. Big O notation describes how an algorithm's running time or resource use grows as the input size becomes large. When we say an algorithm is big O of n squared, or n log n, we are not giving an exact time, but describing its dominant growth pattern and ignoring constant factors and smaller terms. Big O gives an upper bound on how fast the running time can grow, acting like a safety guarantee that it will not grow faster than a certain rate, even if details vary with implementation or hardware. When we analyze algorithms, Big O notation describes how their running time grows as the input gets larger. If you search for a book by checking each one in order, the time grows in direct proportion to the number of books, which is called Big O of n. If the books are sorted and you repeatedly jump to the middle, cutting the remaining options in half each time, the time grows much more slowly, which is called Big O of log n. In both cases, Big O focuses on the overall growth pattern for large inputs and ignores constant factors and smaller terms. Big O notation describes an upper bound on how an algorithm's running time grows rather than its exact behavior, and it is intentionally conservative. Saying an algorithm is Big O of n squared means that for large inputs, its running time will not grow faster than some constant times n squared, even if it often runs faster in practice. This worst-case focus is important for comparing algorithms and planning for heavy load or peak traffic. In practical terms, it helps engineers reason about scalability, since an algorithm with n-squared growth will eventually become slower than one with linear growth as input size increases. By emphasizing these upper bounds, Big O lets us ignore small details and concentrate on the main growth pattern that drives long-term performance. Python code, Big O upper bounds. We can demonstrate Big O upper bounds by timing how algorithms run as we increase the input size. By comparing an algorithm whose running time grows in a straight line with input size to one whose running time grows with the square of the input size, we can clearly see the difference between linear and quadratic growth. These timing comparisons show that Big O describes a safe upper limit on performance, telling us how quickly running time can grow in the worst case as the input becomes larger. The commented line about installing NumPy, Matplotlib, and Seaborn with pip is mainly for users working outside of Google Colab. In Colab, these libraries are already installed, so you do not need to run that installation step. The comment simply reminds users in other environments to make sure these tools are available for data manipulation and visualization before running the code. In this example, we use Python's time module from the standard library to measure how long code takes to run. The module provides functions that let us record the time just before and just after a function executes. By subtracting these two times, we can calculate the function's execution time. This measurement is important for evaluating performance and understanding how an algorithm's running time grows as the input size changes. This description explains a function that adds up all the numbers in a list. It begins with a running total set to 0, then goes through each number in the list and adds it to that total. After every number has been processed, the function returns the final total as the sum of the list. Because it looks at each element only once, its running time grows linearly with the length of the list. The quadratic pairs function is an example of an algorithm that runs in quadratic time, meaning its work grows with the square of the input size. It begins by setting a counter to 0, then uses a nested loop where the outer loop goes through each element of the list, and the inner loop goes through the list again for each outer element. Inside the inner loop, it performs calculations with pairs of elements. But because everything is multiplied by 0, the counter never changes. In the end, the function returns 0, serving mainly to illustrate the quadratic loop structure rather than to produce a meaningful result. We choose several input sizes such as 200, 400, 800, and 1600 to see how our functions perform as the amount of data increases. These different lengths let us observe how running time changes when the input grows. By using this range of sizes, we can clearly compare how a function with linear time complexity grows versus one with quadratic time complexity. To get ready to measure how long our functions take to run, we first create two empty lists. One list will hold the running times for the linear function, and the other will hold the running times for the quadratic function. By recording the times separately in this way, we can clearly compare how the execution time of each function grows as the input size increases. For each input size, we first create a list of numbers from 0 up to that size to serve as our dataset. We then record the current time using a high-resolution performance counter. Call the linear sum function on this list to compute the total of all its numbers and record the time again when it finishes. The difference between the end and start times gives the execution time of the linear sum function for that input size. We store each of these measured durations in a list so we can analyze how the running time changes with different input sizes. We measure how long the quadratic pairs function takes to run by recording the current time before and after it executes. The starting time is captured using a precise performance counter. Then the function is called with the data list. Because this function has quadratic time complexity, its running time increases quickly as the input grows. After it finishes, we record the time again and subtract the start time from the end time to get the elapsed duration. This measured time is then added to a list so we can observe how the execution time changes for different input sizes. We begin by printing a header line that explains the layout of our timing results table. It shows 3 columns: the input size, the time in seconds for the linear function, and the time in seconds for the quadratic function. This structure makes it easy to read the results and directly compare how the two functions perform as the input size changes. The code steps through 3 lists at the same time, one for input sizes, one for the running times of a linear algorithm, and one for the running times of a quadratic algorithm. For each group of values, it prints a line showing the input size, the linear time, and the quadratic time. The times are formatted to 6 decimal places, so they are easy to read and compare. This makes it straightforward to see how the running times of the two algorithms grow as the input size increases. The final note explains how the timing results match their big O upper bounds. It says the linear function has time complexity on the order of n, so its running time increases in direct proportion to the input size. In contrast, the quadratic function has time complexity on the order of n squared, so its running time grows much faster as the input gets larger. These Big O descriptions give a safe upper limit on how each function's performance scales. This script illustrates Big O notation by comparing a linear time function with a quadratic time function as input size increases. The linear function simply sums the elements of a list, while the quadratic function processes all pairs of elements. As the input size doubles, the linear function's running time grows in direct proportion, but the quadratic function's time grows much faster. The measured times are shown alongside input sizes to highlight how linear time is classified as order n and quadratic time as order n squared, demonstrating how Big O gives an upper bound on algorithm performance. Theta tight bounds. Theta notation describes an algorithm's running time by giving both an upper and a lower bound on its growth. Saying an algorithm runs in theta of some function means that for large inputs, its running time increases at essentially the same rate as that function up to constant factors. This makes theta more precise than Big O or Big Omega alone, and helps capture the algorithm's true efficiency. Theta bounds describe algorithms whose running time grows at the same rate as a given function as the input size increases. You can think of it like a t-shirt factory, where the total time mainly depends on how many shirts need printing, not on small fixed tasks like starting the machine. If each shirt takes the same amount of time, the total time increases directly with the number of shirts. In the same way, when an algorithm is theta of a function, its running time is tightly and proportionally linked to that function, not just loosely related. Theta notation is useful for comparing algorithms that solve the same problem, because it focuses on their fundamental growth rates instead of minor implementation details. Two algorithms, such as different sorting methods, may have different constant factors, but still behave similarly for large inputs if they share the same growth rate. When one algorithm's work grows according to a slower growing function, it will be more efficient in the long run, regardless of hardware or programming language. By using theta notation, we ignore small variations and see the true relationship between input size and the amount of work an algorithm must do. Python code theta tight bounds. In this lesson, you will use simple counting loops to demonstrate theta tight bounds and see how the amount of work grows directly with the input size n. You will compare two different algorithms that fall into the same theta classification to understand why they are considered to have the same growth rate. To support this analysis and visualization, you will also install and use the Python libraries NumPy, Matplotlib, and Seaborn. We begin by importing the time module so we can measure how long operations take to run. This module offers functions that let us record the moment an algorithm starts and the moment it finishes. By comparing these two times, we can calculate the elapsed time. This allows us to evaluate and compare the performance of different algorithms. This function performs a simple counting task. It begins by setting a counter to 0, then runs a loop exactly n times. In each pass through the loop, it increases the counter by 1 to represent a fixed amount of work. After the loop finishes, it returns the final value of the counter, which confirms how many operations were carried out. Consider a function that takes an integer input and uses it to run two separate loops. It starts by setting a counter to 0, then runs the first loop exactly n times, increasing the counter by 1 each time. After that, it runs a second loop, again n times, and again increases the counter by 1 on each iteration. In total, the function performs 2 times n basic operations, and it returns the final counter value to show this total amount of work. We use a helper called the time function to measure how long another function takes to run. It first records a precise start time using a high-resolution timer, then calls the target function with the given input size and saves its output. After the function finishes, it records the end time and subtracts the start time to get the elapsed time in seconds. The helper then returns both this elapsed time and the function's result, so we can examine performance and output together. In this example, we set the input size to 2 million items. This large value represents how many elements each algorithm must process. Using such a big input allows us to clearly measure and compare their performance. It also shows how the amount of work each algorithm does grows as the input size increases, which is key to understanding their efficiency in real situations. We begin by timing the single loop algorithm using a timing function that takes the single loop work function and the input size n. This measures how long the single loop takes to run for that specific input size. The timing function returns the elapsed time stored as the single time and the number of operations performed stored as the single result. With these values, we can later compare the performance of this single loop algorithm to other algorithms using the same input size. We now measure how well the double loop algorithm performs using a fixed input size. To do this, we call a timing helper that runs the double loop work with the chosen input size. The helper returns how long the double loop took to execute and the result it produced. We store both the execution time and the computed result so we can later compare performance and report the outcomes. We report the input size, then show how many operations each algorithm performs, first for the single loop and then for the double loop. We also print the time each loop takes and compute the ratio of the double loop time to the single loop time. From these measurements, we conclude that both algorithms have a theta of n classification, meaning their running time grows linearly with the size of the input. This script illustrates theta tight bounds by comparing two simple algorithms that both grow linearly with input size. One function runs a single counting loop, while the other runs two similar loops, doing about twice as much work. Using Python's timing tools on a large input, you see the single loop finish in some time and the double loop take roughly twice as long. This shows that both algorithms are theta of n, meaning their running time increases in direct proportion to the input size. The printed results include the number of operations, the time for each function, and the ratio of their times, highlighting this linear relationship. Omega lower bounds. Omega notation gives a lower bound on the work an algorithm must do as the input size grows. Saying an algorithm is omega of some function means that, beyond a certain input size, it will always take at least that much time or space, no matter how well it is implemented. You can think of omega as the performance floor that the algorithm cannot consistently beat for large inputs. For example, if you must check every item in a list to confirm a value is not present, the time required is at least proportional to the number of items, which is described using omega notation. Omega as a lower bound describes the minimum running time any algorithm must take for a given problem, not just how one specific algorithm behaves. For example, if you are checking tickets at a concert, you must look at each ticket, so the time needed grows with the number of people. In the same way, if solving a problem requires examining every input element, the running time must grow at least in proportion to the input size. Thinking in terms of omega helps you see whether performance limits come from the algorithm's design or from the fundamental nature of the problem itself. Omega notation gives a lower bound on an algorithm's growth, complementing big O, which gives an upper bound. Together, they help define how fast an algorithm can grow in the best and worst cases. When the upper and lower bounds match, the growth rate is well understood, but even when they do not, omega still tells us the fastest possible rate for any algorithm solving that problem. This helps us avoid aiming for impossible performance and instead focus on realistic optimizations, much like recognizing there is a minimum time required for tasks such as baking or traveling. Reading code complexities. Counting key operations. To estimate how long code will run, focus on counting key operations such as accessing list elements, comparing values, or doing calculations. Pay attention to actions that repeat or grow as the input size increases, rather than every small detail. For example, in a function that processes student records, you would count how many times it checks each record or updates counters. This abstract view of the work the function performs, independent of any specific system or language, allows you to classify its time complexity effectively. To count key operations in an algorithm, focus on how often important actions occur as the input size grows. For example, scanning an entire list of length n leads to a number of comparisons and assignments that increases in direct proportion to n, while checking only the first element always does the same amount of work no matter how long the list is. The aim is not to count every single operation exactly, but to understand how the total work scales with input size and to relate that growth to complexity classes such as constant time or linear time. With experience, you start to think about algorithms in terms of how many key operations they perform. And this mindset applies to real systems, not just exercises. For example, if a customer service system must look up and compare every order, then doubling the number of orders roughly doubles the work. In contrast, a system that only checks today's totals does about the same amount of work, no matter how much historical data exists. By translating processes into counts of repeated actions, you can see their underlying work patterns. This skill is essential for understanding time complexity and comparing how well different implementations scale. Python code, counting key operations. In this lesson, we will look at simple Python functions and count how many key operations they perform. We will compare functions that do a constant amount of work with those whose work grows in proportion to the size of a list, using small list examples. By printing out these operation counts, we connect what the code is doing to the idea of time complexity. We will also install common data and machine learning libraries, such as NumPy, Pandas, Matplotlib, Seaborn, scikit-learn, PyTorch, and TensorFlow to support further experiments. Consider a function that checks whether the first element of a list matches a target value while counting how many basic operations it performs. It increments a counter when it accesses the first element, then increments it again when it compares that element to the target. The function returns both the result of the comparison and the total number of operations. This example illustrates constant time complexity because the number of operations does not change even if the list becomes longer. We define a scan all elements function that takes a list of numbers and a target value and tracks how many basic operations it performs. It starts with an operation counter at 0 and a flag that says the target has not been found. As it loops through each element, it counts the cost of accessing the element and comparing it to the target. If the element matches the target, it records the extra work for that comparison, sets the flag to found, and continues or stops as designed. In the end, the function returns whether the target was found and the total number of operations used during the scan. We begin by creating two lists that represent different input sizes. The small list contains the numbers from 0 to 9, and the large list contains the numbers from 0 to 999. Both lists are generated using a function that produces a sequence of numbers and then converts that sequence into a list. These two lists let us see how the same functions behave with small versus large inputs, so we can compare how many operations are needed in each case. We choose a target value of 5 because it appears in both the small and large lists used in our example. Using a target that is present in both lists lets us clearly show how each search function behaves when the target is actually found. This setup allows us to measure and compare how many operations each function performs under the same successful search condition. We analyze a function that only checks the first element of a list by measuring how many operations it performs. We run it once with a small list and a target value, recording both the result and the operation count. Then we repeat this with a larger list and again record the result and the number of operations. Comparing these counts shows that the function does the same amount of work, no matter how long the list is, which demonstrates constant time complexity. We measure how many operations it takes to find a target value in a list by using a scan all elements function that checks each item one by one and counts each access and comparison. First, we do this on a small list and record whether the target is found and how many operations it required. Then, we repeat the same process on a larger list and record those results. Comparing these counts shows that the number of operations increases in direct proportion to the size of the list, which illustrates the idea of linear time complexity. We compare how many operations different functions perform on small and large lists to illustrate time complexity. First, we count operations for a function that only checks the first element of a small list. Then do the same for a large list, showing that the count stays the same and therefore has constant time complexity. Next, we count operations for a function that scans every element in a small list and then in a large list, showing that the number of operations increases with list size. This growing operation count demonstrates linear time complexity. This script shows how counting key operations in Python functions helps explain time complexity. One function only checks the first element of a list, so it always does the same small number of operations no matter how long the list is, which illustrates constant time. The other function scans every element in the list looking for a target value. So the number of operations grows with the list size, which illustrates linear time. By comparing the operation counts for small and large lists, you can clearly see the difference between constant and linear time complexity. Combining sequential steps. When analyzing a function's running time, you can think of it as a sequence of steps, such as input validation, searching, and formatting the result, each with its own time cost. In complexity analysis, you add these costs, but Big O notation focuses only on the part that grows the fastest as the input size increases. This means that even though several steps contribute to the total time, the step with the highest growth rate is what really determines the overall complexity. When analyzing a function's time complexity, you can think of each major section separately. A loop over a list of customer records contributes a linear time cost, while a fixed task like logging is constant time. If you later have another loop over the same list, the total time complexity is still linear, because two linear passes still grow in proportion to the list size. The constant time work in between does not change this overall linear behavior. When analyzing how a function's running time grows, focus on the part that increases the fastest as the input size grows. A function may start with a simple scan through data, but a later step that compares every item with every other item will eventually dominate the total time. As the data set becomes large, this most intensive step is what really determines the function's behavior. In practice, the overall time complexity is driven by the operation whose cost grows the quickest with input size. Python code combining sequential steps. This material focuses on understanding overall time complexity by combining sequential steps. It contrasts a linear step with a quadratic step and explains how, when they are executed one after the other, the quadratic behavior dominates the total running time. It also suggests printing simple timing results for different input sizes to observe how each step grows and how their combined performance changes as the input increases. Standard libraries are enough for this comparison, so no special installation is required. We use Python's time module to measure how long parts of our code take to run. This module provides functions that let us record the time just before a function starts and right after it finishes. By comparing these two times, we can calculate the function's execution time. This information helps us understand and evaluate the performance of our code. Is function makes two linear passes over a list to compute a sum. It starts with a running total set to 0, then loops through the list once, adding each element to the total. It then loops through the same list a second time, again adding each element to the running total. The final result is the sum of all elements in the list counted twice, illustrating a linear time operation that is performed sequentially 2 times. The function begins by setting a running total to 0, and then makes a single pass through the list, adding each element to this total. After that, it uses a pair of nested loops that each go over all indices of the list. And inside these loops, it multiplies the current element by 0 and adds the result to the total. Because multiplying by 0 has no effect, this nested section does not change the final value. However, it still demonstrates quadratic time complexity due to the structure of the two loops. In the end, the function returns the total, which is determined entirely by the initial single pass through the list. Is function measures the average running time of another function. It uses a high-resolution timer to record the start time, then repeatedly calls the target function with a given data list a specified number of times. After the loop finishes, it records the end time with the same timer. It then subtracts the start time from the end time and divides by the number of repeats. The result is the average time the function takes to run. We begin by choosing a few input sizes, such as 50, 100, and 200, to represent different amounts of data. These values let us test how long our functions take to run as the input grows. By comparing execution times across these input sizes, we can observe how each function's time complexity changes with larger or smaller datasets. The code begins by printing a header message that tells the user the program will compare two computational methods. One method makes two linear passes over the data, and the other makes one linear pass followed by a quadratic operation. This introduction prepares the listener to think about how these different approaches affect performance as the input size grows. We test performance by looping over different input sizes and, for each size, creating a list of numbers from 0 up to 1 less than that size. This list serves as the data for two functions we want to compare. We time the function that makes two linear passes over the data, repeating it many times to get an average, and then time the function that combines one linear pass with a quadratic operation, averaging over fewer runs. Finally, we report the input size and the average time for each function, formatted consistently, so we can see how their performance changes as the data grows. This script uses Python's time module to compare how long two different functions take to run as the input list grows. One function makes two separate linear passes over the list, so its time increases roughly in proportion to the list size. The other function combines a linear pass with a nested loop over the list, which gives it quadratic time complexity. The script measures average execution times for both functions on lists of 50, 100, and 200 elements. The results show that while the linear work grows modestly with input size, the quadratic part causes the runtime to increase much more rapidly, dominating the overall performance. Nested loops and calls. Beyond single loops, nested loops and function calls play a major role in an algorithm's time complexity. A nested loop is one loop inside another, and its cost depends on how many times the inner loop runs compared to the input size. When both loops grow with the input, their work multiplies, which can make the algorithm much slower as the input increases. Seeing nested loops as stacked layers of repeated work helps you recognize when an algorithm may not scale well. Nested loops can behave differently depending on how the inner loop's range changes with the outer loop's value. For example, in a tournament where each player faces every other player only once, the inner loop shrinks each time, but the total work still grows roughly with the square of the number of players. This means that even when the inner loop does not always run over the full input size, the overall number of operations can still be quadratic. When analyzing code, focus on how the total work scales with input size, since nested loops often lead to quadratic or even higher growth in operations. To understand time complexity when functions and loops interact, think of the total cost as the number of loop iterations multiplied by the cost of the function being called. If the function itself loops over the input, it effectively acts like an inner loop and increases the overall complexity. If the function only does a fixed amount of work, its cost is constant and the loop's behavior dominates. By examining each loop and each function call in this way, you can break complex code into simpler parts and determine its overall time complexity. Python code, nested loops, and calls. We will explore time complexity by using simple nested loops that compare pairs of elements and by placing function calls inside these loops to see how their costs combine. For different input sizes, we will count and print how many operations are performed, so we can observe how the number of operations grows as the input increases. This helps build an intuitive understanding of how nested structures and repeated function calls affect overall performance. Only standard libraries are needed, so no special installation is required. We define a function called constant work that takes two students and a distance in feet, then converts that distance to inches by multiplying by 12 and adding 6. This calculation is the same every time, no matter what values are passed in. The function then returns a message that names the two students being checked and reports the computed distance in inches. This example is used to illustrate a constant time operation within nested loops. We define a function that goes through all unique pairs of students and counts how many constant time operations it performs. It starts by setting an operations counter to 0 and finding how many students are in the list. The function then uses two nested loops. The outer loop picks the first student in a pair, and the inner loop picks the second student, always starting after the first to avoid repeating pairs. For each pair, it calls a constant work function with that pair and a fixed distance of 3 feet, then increases the operations counter. At the end, the function returns the total number of operations, which equals the number of unique student pairs processed. This linear helper function counts how many students are in a list by starting a counter at 0 and then looping through each student. For every student it encounters, it increases the counter by 1. After the loop finishes, it returns the final counter value as the total number of students. Because it processes each student exactly once, its running time grows in direct proportion to the size of the list, which is called linear time complexity. The outer with helper function illustrates nested behavior by using a separate helper function to count work. It begins by setting a counter for the total number of operations to 0, then loops through each student in the list. For every student, it calls the linear helper function on the full list of students and adds the number of operations that helper performs to the running total. In the end, it returns this total, which reflects how many operations were carried out and highlights the complexity created by the nested structure. We define a list of input sizes using the numbers 3, 5, and 8 to represent different amounts of input data for testing our functions. These small sizes keep the results easy to read and interpret. Using them helps us clearly see how the number of operations increases as the input size grows. We test how the number of operations grows by running our code on groups of 3, 5, and 8 students. For each group size, we create a list of student identifiers and pass it to a function that compares every pair of students using nested loops, which shows quadratic time behavior. We also call another function that uses a helper function inside a loop, giving a different nested pattern and its own operation count. Finally, we print the group size and the operation counts from both functions so we can see how the work increases as the input size grows. This script uses a simple example of comparing pairs of students to explore how nested loops and function calls affect time complexity. It includes a constant time function that computes a distance between two students, then builds on it with two main functions. One function checks every possible pair of students with a nested loop, leading to quadratic growth in the number of operations. Another function calls a linear helper function inside an outer loop, creating a nested structure that results in cubic growth. By running these functions on groups of 3, 5, and 8 students and printing the operation counts, the script shows how different loop patterns scale very differently as input size increases. Comparing algorithm growth. Core complexity classes. Big-O notation compares algorithms by how their running time grows as the input size increases. Constant time algorithms take about the same time no matter how large the input is. Logarithmic time algorithms grow slowly as the input grows, and linear time algorithms grow in direct proportion to the input size. These three types, constant, logarithmic, and linear, are considered efficient and are preferred for large inputs over algorithms whose running time grows more quickly. As we move beyond linear time algorithms, we encounter running times that grow faster than the input size, which matters a lot for large problems. Linearithmic time, often described as n times log n, is only slightly more expensive than linear and is still practical, as in many divide and sort methods. Quadratic time grows with the square of the input size, so doubling the input makes the work about 4 times larger. And cubic or higher polynomial times grow even more steeply and quickly become impractical. For large inputs, a linearithmic algorithm will be much more efficient than a quadratic one, even if their performance looks similar on small inputs. Exponential and factorial time algorithms quickly become impractical as input sizes grow, because the number of possibilities they must consider explodes. Exponential algorithms may double their work with each added feature, and factorial algorithms grow even faster as each new item multiplies the number of arrangements. In contrast, polynomial time algorithms, such as linear or quadratic ones, scale much more reasonably and remain efficient for larger inputs. Understanding these different complexity classes is essential for choosing algorithms that will scale well in real-world applications. Python code, core complexity classes. This material focuses on illustrating core algorithm complexity classes by comparing how long they take to run as input size grows. It highlights constant time, linear time, quadratic time, and exponential time behaviors. By observing how their running times increase with larger inputs, learners can clearly see and compare different patterns of algorithm growth. The comment in the code mentions installing NumPy, Matplotlib, and Seaborn, but explains that they are not required for this simple example. This means the core code is intentionally kept straightforward and does not depend on these external libraries. The comment mainly serves as a suggestion for users who may later want to extend the code with tools for numerical work or data visualization in more complex situations. The code starts by importing Python's time module, which provides tools for working with time. In this context, it is used to measure how long different functions take to run. By recording the time just before a function starts and right after it finishes, we can calculate how long the execution took. This duration lets us compare the performance of different algorithms. This example function illustrates constant time complexity. It initializes a total, then runs a loop that executes exactly 10 times, adding 1 to the total each time, and finally returns the result. The crucial idea is that the number of operations is fixed and does not change with the size of the input. Because its running time stays the same no matter what input you provide, this function is considered to run in constant time. This function runs in linear time, meaning its running time increases in direct proportion to the input size n. It begins by setting a running total to 0, then loops from 0 up to, but not including n. In each loop step, it adds the current index to the running total. By the end of the loop, it has computed the sum of all integers from 0 to n minus 1, and it returns this final total as the result. This example function is built to show quadratic time complexity. It starts with a running total set to 0, then uses an outer loop that goes from 0 to the input size n. Inside that, an inner loop also runs from 0 to n, so for every step of the outer loop, the inner loop runs completely. In each pass of the inner loop, it adds the current loop positions to the total, and when all loops finish, it returns this accumulated value. Because the two loops are nested and each depends on n, the total number of operations grows with n squared, which is why the function has quadratic time complexity. This function computes Fibonacci numbers using recursion, which has exponential time complexity. It first checks if the input is 0 or 1 and directly returns that value as a base case. For larger inputs, it calls itself twice, once with the input -1 and once with the input -2, then adds those results. This process continues until all calls reach the base cases and their results are combined to get the final Fibonacci number. The method is computationally expensive because many values are recalculated repeatedly, causing the number of operations to grow very quickly as the input increases. This helper function measures how long another function takes to run. It first records the current time using a high-resolution performance counter, then calls the target function with the given input size. After the function finishes, it records the time again. By returning the difference between the end and start times, it gives the execution duration. This makes it possible to compare how fast different algorithms run for various input sizes. We choose 3 input sizes, 10, 50, and 100, to test how our functions perform with different amounts of data. These values let us see how the runtime changes as the input grows, while still keeping the computations quick enough for a simple demonstration. This setup helps us compare how each function behaves under increasing workload without making the tests too slow or complex. The program starts by printing a header message that tells the user it will compare different complexity classes using simple timing measurements. This introduction prepares the user for the results that follow. The output will show how various algorithms perform as the input size increases, helping to illustrate how their running time grows. We loop over a list of input sizes, and for each one, measure how long it takes to run the constant time function, the linear time function, and the quadratic time function using a timing helper. The measured times are stored separately for each type of function. We then print the current input size along with the 3 measured times, rounded to 6 decimal places. This lets us directly compare how the running time grows with input size for constant, linear, and quadratic time complexities. We test an exponential time Fibonacci algorithm using small input sizes, such as 10, 20, and 25, so the program does not take too long to run. For each of these inputs, we measure how long the algorithm needs to compute the Fibonacci value. We then print the input size along with the time taken. This simple experiment demonstrates how quickly the running time grows as the input increases, which is the defining feature of exponential growth. This script measures how the running time of different algorithms grows with input size, illustrating constant, linear, quadratic, and exponential time complexity. The constant time function stays fast because it always does a fixed amount of work. The linear function gets slower in direct proportion to the input size, while the quadratic function, with nested loops, slows down much more quickly as it processes pairs of elements. The exponential function, implemented with a recursive Fibonacci calculation, becomes impractically slow even for moderately large inputs. By printing these timings, the script lets you observe how each complexity class scales as the input increases. When O(n) log n beats O(n) squared. An algorithm whose running time grows like n times log n is more efficient in the long run than one that grows like n squared, even if it looks more complex or has a larger constant factor. For small input sizes, the n-squared algorithm might actually run faster because of better constants or optimizations. However, as the input size becomes very large, n-squared increases much more quickly than n times log n. Beyond some point, the n times log n algorithm will use far fewer operations, and this advantage grows with larger inputs. This long-term behavior is what matters most in algorithm analysis, especially for real systems that handle large amounts of data. When organizing a large collection of documents, we can use an approach that compares every document with every other, which grows with the square of the number of documents. Or we can first sort the documents, which grows like the number of documents times the logarithm of that number, and then compare within the sorted order. For small collections, the difference between these two strategies is small, and the simpler square growth method may seem fine, but as the collection grows to thousands or millions of documents, the square growth method becomes far too slow because each new document must be compared with an ever larger set. The method that grows like n times log n stays much more efficient at large scale, which is why algorithms with lower growth rates are preferred, even if they look more complex at first. In large real-world systems, choosing efficient algorithms is crucial because performance changes as the amount of work grows. For example, a simple approach that compares every possible route or record grows roughly with the square of the number of items, while a more efficient method that organizes data, such as by region or time, grows more like the number of items times the logarithm of that number. Both approaches may seem fine for small cases, but the slower one quickly becomes impractical at scale. Understanding that algorithms with growth, like n times log n, eventually outperform those that grow like n squared helps you select methods that stay efficient as data and user bases increase. Python code. When O(n) log n beats O(n) squared. We want to compare algorithms whose running times grow like n times log n and n squared, and show that n times log n eventually becomes faster. As the input size n increases, the n squared algorithm's work grows much more quickly than the n times log n algorithm. There is a crossover point where, for small n, n squared might be acceptable. But beyond that size, the n times log n algorithm clearly does less work. Understanding this crossover helps us see why, for large inputs, an algorithm with n times log n growth is more efficient than one with n squared growth. This line installs 3 Python libraries: NumPy, Matplotlib, and Seaborn. NumPy is used for numerical computations, while Matplotlib and Seaborn are used for data visualization and statistical plotting. Even though they are not directly used in the given code, they are common tools in data analysis and scientific computing. They may be useful later for exploring or visualizing the results produced by the code. We begin by importing the math module from Python's standard library so we can use its built-in mathematical functions. This module includes tools for working with logarithms, which we will need to model operations that have logarithmic complexity. Using the math module lets us perform these calculations efficiently and accurately within our script. This function is meant to simulate an algorithm whose work grows on the order of n times the logarithm of n. It keeps a running total of operations, then loops from 1 up to n. For each value, it computes the base 2 logarithm of the index plus 1, rounds it down to an integer, and uses that as the number of inner steps to perform. In each of those inner steps, it increments the total by 1. The final returned total represents the simulated number of operations for an n log n time complexity. This function represents an algorithm whose work grows with the square of n. It keeps a running total of operations and uses 2 nested loops, where the outer loop runs n times and the inner loop also runs n times for each outer pass. Each time the inner loop runs, the total is increased by 1. When both loops finish, the function returns this total, showing that the number of operations is proportional to n squared. The code uses a set of input sizes, such as 50, 100, 200, 400, and 800, that are small enough to compute easily, but large enough to show performance differences between 2 algorithms. By testing these increasing sizes, we can observe how each algorithm's running time grows as the input becomes larger. This makes it easier to compare their growth rates and understand which algorithm scales more efficiently. The code first prints a header line that labels the columns of data that will appear next. It defines 3 columns: the input size n, the number of steps for the n log n algorithm, and the number of steps for the n squared algorithm. This header clarifies what each column represents and makes it easier to interpret the results. As more lines of data are printed, the header helps you compare how the 2 algorithms perform as the input size increases. We loop through each input size and for each one, use our earlier function to estimate how many operations an algorithm with running time proportional to n times log n would perform. We record this as the step count for that input size. We then use a second function to calculate the number of operations for an algorithm whose running time grows with n squared. Finally, we print the input size along with both step counts so we can compare how the 2 algorithms scale as the input size increases. The final note in the code emphasizes the point where the growth of n squared becomes larger than the growth of n times log n as n increases. It reminds us that even if n times log n may at first appear slower, it eventually leads to more efficient performance than n squared for large inputs. This idea is important for understanding and comparing the efficiency of algorithms with different growth rates. This script compares 2 algorithms, one whose running time grows like n times log n, and another whose running time grows like n squared. It calculates how many operations each algorithm performs for several increasing input sizes. As the input grows, the n squared algorithm's operation count increases much faster than the n log n one. Although n log n may not look better for very small inputs, as n becomes larger, it clearly outperforms n squared. This illustrates the crossover point, where the more efficient growth rate leads to better performance for large inputs. Dropping constants and terms. In asymptotic analysis of algorithms, we ignore constant factors and lower-order terms and focus on how performance grows as the input size becomes large. Even if one algorithm uses several times more operations than another, but follows the same growth pattern, they belong to the same complexity class. In Big O notation, multiplying by a constant or adding smaller terms does not change the classification, because the dominant term controls the overall behavior. This perspective lets us compare algorithms by their long-term efficiency rather than by specific implementation details. Consider two ways of processing customer orders where one has a fixed setup cost and the other adds extra security checks, but both scan each order once. At small scales, the setup and extra checks may seem important, but as the number of orders grows to millions, these constant differences become negligible. What really matters is that both methods scale in direct proportion to the number of orders, so doubling the orders roughly doubles the processing time. Because of this linear scaling, both are classified as having time complexity on the order of n, and we ignore constant setup costs and minor terms when analyzing performance for large workloads. When comparing algorithms, we focus on how their running time grows with input size and ignore constants and smaller terms. For example, an algorithm whose time grows like n times log n will eventually beat one that grows like n squared, even if the n squared algorithm is faster on small inputs. This happens because the n squared term increases much more quickly as n gets large. Big O notation captures this idea by emphasizing the dominant term that controls performance at scale. This perspective is essential when designing scalable systems, such as social networks or data analytics platforms, where long-term efficiency matters more than initial speed. Python code, dropping constants and terms. In Big O notation, we ignore constant factors and smaller extra terms because they do not change the fundamental growth pattern of a function. For example, two linear functions may have different constant multipliers and added terms, but they both still grow in direct proportion to the input size. As the input becomes large, the dominant growth pattern, such as linear, quadratic, or logarithmic, matters far more than specific constants. This is why Big O classification focuses on the overall rate of growth, not on constant differences or lower-order terms. This line is suggesting that you install the NumPy and Matplotlib libraries, which are widely used in Python for numerical calculations and data visualization. They are not directly required by the current code, but may be useful if you later add features for analysis or plotting. In short, it is a reminder to make sure these packages are available in your environment for possible future extensions of the script. We begin by importing the time module, which provides tools for working with time in a program. In this context, it is used to measure how long specific operations take to run. By recording these execution times, we can compare the performance of different functions. This helps us evaluate their runtime efficiency and choose faster or more efficient implementations. This example describes a function that runs a simple linear process. It starts by setting a running total to 0. Then repeats a basic operation a specified number of times. In each repetition, it increases the total by 1. After completing all repetitions, it returns the final total. Because the work done grows directly in proportion to the number of repetitions, this illustrates a process with linear time complexity. This function models processing a set of orders with a heavier workload. It starts with a total set to 0, then runs a loop 3 times the number of orders, increasing the total by 1 each time to represent 3 times the effort per order. The final total represents the completed workload. This example shows that increasing the constant amount of work in a linear process makes it slower in practice, but does not change its overall Big O classification. This helper function measures how long another function takes to run for a given input size. It first records the current time using a high-resolution performance counter, then calls the target function with the chosen input size. After the function finishes, it records the time again and computes the difference between the 2 times. This difference is the execution time, which can be used to compare how fast different functions run under the same conditions. We will test 2 different linear functions using a set of input sizes that represent different numbers of customer orders. These input sizes are 1,000, 5,000, 10,000, and 50,000 orders. By running both functions on each of these sizes, we can compare their performance and see how they scale as the number of orders increases. The code first prints a header line that explains the performance data that will follow. It labels the input size, the runtime of the basic linear function, the runtime of the heavier linear function, and the heavier function's runtime divided by 3. This makes it easier to compare how the 2 functions perform as the input size grows. We test different input sizes by timing a simple linear order processing function and a heavier linear function. After measuring both runtimes, we divide the heavier function's time by 3 to adjust for its larger constant factor. We then report the input size, both runtimes, and the adjusted ratio with consistent numeric formatting. This experiment shows that despite different constant factors, both functions share the same linear growth pattern, which is what matters for Big O classification. This script compares 2 linear functions to show why constants and smaller terms are ignored in Big O notation. Both functions process customer orders with a loop, but one runs a loop that is 3 times longer, so it takes more time for the same input size. When you measure their runtimes for different numbers of orders, the second function is slower by a constant factor. However, if you divide its runtime by 3, its growth pattern closely matches the first function. This demonstrates that Big O focuses on how runtime grows with input size, not on constant multipliers, so both functions are considered linear. In this lecture, you learn to explain the meaning of Big O, Big-Theta, and Big Omega in the context of algorithm analysis, determine the time complexity class of simple Python functions by inspecting their structure, and compare 2 algorithms using Big O notation to justify which is asymptotically more efficient. In the next lecture, Lecture B, we will go over math for analysis.
Thank you for your attention. See you all in the next lecture.